Okay, so we've got the 6.1 review sheet here. Just going to start in the top left-hand corner, where it's asking you for the equation, or how we turn that equation into a triangle so you can rearrange it. So speed equals distance over time is how you'll see it in your front of your paper. Because distance is already on the top of time, distance stays up the top and speed moves down, so it's d over s and t. And then if you wanted to work out distance, it's distance equals speed times time, because they're together. If you want to work out speed, it's distance over time, and the same if you want to work out time, it's distance over speed. Distance is measured in meters, time is measured in seconds, and speed is measured in meters per second. This is a typical question where you've got displacement, and we'll talk about vectors and scalars in a bit, but displacement is how much it moves in a particular direction, and this is the journey of a bus. So you've got time on the bottom. This is called a distance time graph. Okay, so describe the journey. Well, from 0 to A is constant speed. That straight line represents constant speed, and then it actually stops there because it's not covering any distance as time passes. So there's no distance being covered as time passes, and then it actually starts traveling back at a constant speed in the other direction. So it comes back in the other direction, stops for a bit, C to D, and then it's a less steep line. So even though it's a constant speed, it's not as fast as this, because you can see it's covering 10 meters there in sort of 5 seconds, where it's covering 5 meters there in, say, I don't know, let's have like 21 minus 16 in 5 seconds, something like that. So the steepness of the line dictates the speed at which it travels. Then we've got some equations again. So it's just asking us, so a lot of maths now, so which is why it's important to work out these, or to remember these triangles. A car travelled 5 meters. So I've got my distance in 30 seconds, I've got my time. What was the car's speed? So speed equals distance over time. Okay, so I cover S, and that's going to be 5 over 30, and that's going to be 0.17 or 0.17 meters per second there. Use the equation, speed equals distance over time. If a car traveling 10 meters, distance is 10. Speed of 25 this time. What's my time? Well, time equals distance over speed, 10 over 25. Time is 0.4 seconds. I know that looks like 0.45. That's actually seconds there. Then we come to acceleration. So I might start by here and then move down here actually. So using the equation, acceleration equals change in velocity over time. So my change in velocity is my initial speed, my final speed, which is v, minus my initial speed, which is u. And we also call them velocities, so that's why the v. So velocity is just a vector of speed. It's the same thing, it's measured in meters per second. So it's v minus u over acceleration times time. So we would work this out. So work out the acceleration of a car in 5 seconds. Well, I know my time is 5, from 25 meters per second to 35 meters per second. So the initial speed is 25, and my final speed is 35. So it's getting faster from 25 meters per second to 35 meters per second. So my final speed is 35 minus my initial speed is 25. So that's going to be 10 there over my time to get my acceleration. So 35 minus 25 is 10 over 5, which gives me 2 meters per second squared, because it's per second, and we'll talk about that in class. Then we go to the bottom, work out the time when the car accelerates 30 meters per second square with a change of velocity of 10 meters per second. So it's giving you the change here, velocity, so that's already 10. So v minus u is all wrapped up in 1, because it's giving you the change of velocity over the acceleration, which is 30 meters per second, and that's going to give us a time of 0.3 seconds. I'm going to go up to the top now, because I've talked about these things, scalars and vectors. Well, a scalar is magnitude without direction, and a vector is magnitude with direction. So you pretty much got a quantity there without a direction, such as speed, mass, time, temperature, distance. And then things with direction are things like your velocity, which is the vector of speed, meters per second for them both. You've got displacement, which is the vector of distance. So distance is just a magnitude. Displacement is a magnitude with direction. And then force has got a direction as well, which we'll come to see probably after Christmas now. Turn the following equation into a triangle to be rearranged. Oh, so this is probably what I should have done before doing the acceleration equations. So this is what's in your book. It's acceleration, change of velocity over time. Just to show you what I was on about there, that's what we was using there and there. Or actually there and there, okay? So this is how you do it. You've got your change in velocity, which is v minus u, and then your acceleration and t there. So because change in velocity is already on the top, it stays up top, acceleration comes down. So what is the letter given to initial velocity is u, the letter given to final velocity v, and then you've got your acceleration, meters per second squared, meters per second, so it's your speed per second, because your speed is meters per second, that's why it's meters per second squared. And then your time is in seconds there. Again, for your triple group, you're going to see this come up in Suvat. And then let's have a look. I'll do this one on the bottom because it chucks in stopping distance. So that is, I'm going to leave that till the end. It says describe the journey of a bus. Now, where we describe the journey of the distance time graph here, I've got a velocity time graph now. So this is your speed against time. So to describe this, I would say from A to B is constant acceleration now, not constant speed, it's constant acceleration because you can see it progressively gets faster. So that's accelerating. Now, instead of that being stationary now, you can see as time passes, it's constantly at 60 meters per second. So now from B to C, I've got a constant velocity. It's actually slowing down now in this velocity. It's getting less. So I got a constant deceleration, we could say there. Okay, it actually goes into the negative there. And then it comes back up from D to E, constant acceleration there. Calculate the distance between 15 seconds and 25 seconds. So I should have taken a photo really of, because they'll give you an equation at the front of your book, but we'll do some practice in class anyway. The distance, if you want to work out distance on a velocity time graph, you just calculate the area underneath the graph. So what I've done here, I've labeled 25 there to 15. So I've got, I got 10 this way, so I got a base of 10, and I got a height of, let's have a look, from minus 40 to 20 is 60. So I've got that, so I've got 10 times 60 gives me 600. And then I've got half times 10 times 40, because your triangle is half times base times height. So we've got half 10 times, well, my increase in height is from 20 to 60, so it's 40, so 10 times 40. And then because it's a triangle, just half it. And then I add the two together, and I get 800 meters. So just finish off this video now. This kind of tagged on at the end about stopping distance. So stopping distance is going to equal thinking distance plus your braking distance. So the time it takes you to think about it and the time it takes you to brake equals the stopping distance. And by that I mean if I was driving and I saw a dog run out on the road, okay, I'm going to think about that first, even though you're talking a couple of seconds, you still think about it first, and then the actual braking distance is from the time my foot hits the brake. They're going to ask you some effects of thinking distance. So what affects thinking distance? Well, if I was on medication or drugs, that's going to affect it. Alcohol consumption is going to affect it, which is why there's a ban on drink driving. Any distractions like mobile phones, friends in the car, switching the radio, sat-nav, things like that is going to affect your thinking distance. This is the time it takes to think about it. And obviously your age, as you get older, you're going to take longer to think about distractions. Then things that affect braking distance, nothing to do with now your thinking distance. This is the time where your foot hits the brake. So the condition of your brake pads, your tyre tread, the weather conditions, the incline. So if you're going uphill, you're going to brake quicker than if you was going downhill, because downhill you've got gravity, the force of gravity. And then you've got the road surface. So if you was on gravel or if you was on tarmac, on grass, all affects your braking distance there, the time it takes to stop whilst hitting the brake. How can the council make roads safer? it's a common question because they like to apply it to safety campaigns. So you've got your speed awareness campaigns, so adverts on the TV. You've got your speed cameras and you've got your speed bumps. They're the top three all the time. And I think that's it. So look, yeah, not bad. 10 minutes. Obviously, you would have stopped and paused this.